Welcome to the third lecture on reliability. So we will discuss in this lecture parameter variation and hard errors and aging. So as you will see, these are all related in kind of the same way. So let's look at the VLSI design process to begin with. So what we do is we consider a large wafer, so 20 to 30 centimeters in diameter, roughly 1 foot. So we coat it with a photoresist. Then what we do is that, so photoresist, if I would look at it, this would look like this. The side view would be like this. Sorry, maybe let me clear off the ink and then we have this photoresist over here. So what happens is that we coat it with it, and then we have a light source. So the light source, basically what it does is that, so you put a mask over here. So pattern gets printed on the photoresist. And the pattern that gets, so this is an optical pattern, but the photoresist is something that reacts with light. So then structures on the VLSI circuit form. Of course, it could be, kind of a positive reaction or a negative, in the sense the parts that are exposed could change their form. Well, the parts that are exposed always change their form, but then the point is that when I wash out the photoresist with an acid, what gets washed out? The parts that are exposed or not? So what I do is I apply a solvent and I wash it out. This process is known as etching. And with etching, what happens is either the parts that are exposed, they wash out, or the parts that are not exposed, they wash out. In either case, it doesn't matter, right? At least from a logical point of view, but of course, physically it matters a lot. So what happens is, let us assume that the parts that are washed out are the parts that were exposed. So the point is that we have patterns like this. If we look at it from the side, so we'll have patterns, we'll have trenches. So the trench is where the basic silicon is exposed. Otherwise, the basic silicon is not exposed. Now, let's say to dope a region, we can spray a dopant, in a gaseous form. So it can either be an N-type gas or a P-type gas, right? Phosphorus type, boron type. We allow the dopants to kind of permeate into the silicon, so get either N-type doped or P-type doped. And then basically what we do is that we again wash out the rest of the areas, and then we can create oxide layers again by a similar process. So what we are basically doing is that we are creating regions of doped regions of, let's say, N-type dope, P-type, and then N-type, that would make a transistor. And then on top of that, we can create a silicon dioxide layer, then implant metal on top of it. The idea is the same. We do this thing that I just described over and over again, where we coat it with a photoresist, we expose light to parts of it, then we wash out the rest, or we wash out the parts that have been exposed. In this case, we are assuming that we wash out the parts that have been exposed. Then we kind of spray dopants or spray metal in a gaseous form. That forms a metal layer, right? Or that forms a dopant layer. And we keep on doing that. So with this, we can create a multi-layer chip. This is the broad idea. So we are essentially patterning and then patterning, so on and so forth, basically using light and chemical solvents. That's the broad idea, that you first coat it with a photosensitive material known as a photoresist. You apply light to it. How do you do that? Well, you have a light source, and then in front of the light source, you put a mask. So the mask will block some light and let the rest pass through. The light that hits the photoresist, it reacts with it, it changes its chemical structure. Then we basically wash out parts of the photoresist and expose the parts that have been washed out to essentially a different kind of an environment, a gaseous environment where dopants can percolate or metal can get deposited. So there are some basic questions, right? So the idea basically here is that you are making an engraving, right? So that's the broad idea, that you are making an engraving. So of course, I would like to make a small correction to what I just said. It is not necessary to use a gaseous medium all the time. It could also be a liquid medium where the liquid, can seep in into the areas that are where the photoresist has been removed. Right? So the process of removal is called etching. So let's not care about whether it's a gaseous effusion or a liquid effusion, but the key idea is that you have removed parts of the photoresist. These parts are exposed, and this is where something can be accumulated. What can be accumulated could be a dopant, or could be a metal, or could be silicon dioxide. It depends on what exactly we want to create. So the question is that we are essentially engraving the surface of the die, or the surface of the die with the photoresist on top of it. We are creating a very fine engraving, in the sense we want to create very, very thin lines, and these lines are essentially a couple of nanometers wide. So can such a fine engraving be done with a blunt knife? Well, let me ask this question. Let's say there's a 10 nanometer feature, right? So which means that it's end to end, it's only 10 nanometers wide. Can you do it with 193 nanometer light or 157 nanometer light? Well, the answer is no, right? Because the point is that you are using light whose wavelength is substantially more than the size of the feature that you are trying to create. Of course, now we have, as of writing this book, we have gone down to around 7 nanometers. So in this case, we are not using 157 nanometer light. We are using light which is, at a much lower wavelength. So for these ultra small features, we are using 13.5 nanometer light, which is in the ultraviolet range. And of course, this will go down to, let's say, maybe 3 nanometers or beyond. But the idea still is that the wavelength lambda of light is significantly more than the size of the feature that we want to create, right? Be it 193, 157 or 13.5, it doesn't matter. In all cases, we are using light whose wavelength is much, much more, 4 times, 5 times, 10 times more than the size of the feature that we want to create. Hence, there will be imperfections because light cannot accurately, let's say we want to draw a rectangle on silicon, that's not going to happen. What's going to happen is that the corners will get rounded. What you'll have is something like this. So we need to further understand that along with the limitations of light, there are limitations of atomic particles as well. Like an atom is roughly 1 angstrom, 0.1 nanometers. So a 10 nanometer feature is roughly 100 atoms laid side by side. And 10, 20 atoms going here and there is not a big deal, but that would create a plus or minus 10% difference in the feature size of the feature, which would have significant consequences in terms of the electrical parameters of the design that we are creating. It could have a very different threshold voltage, for instance. So even placing these atoms side by side, we can't be that accurate. Our doping process is not all that great. Plus, we are using light with a significantly higher wavelength as opposed to the feature size. So all of these things contribute to process variation, which is basically what we want to print is not what we actually print, right? What we want is not what we get. And there are imperfections in the fabrication process, mainly because of the wavelength of light, and also because of the fact that we are trying to place atoms side by side, and placing them side by side that accurately is not possible. There are bound to be inaccuracies in the system. So parameter variation is something that considers process variation, which we just described, which is imperfections in the fabrication process, but also along with that, variations in the runtime conditions. Right? What kind of runtime conditions we will see? Let's first look at process variation, then we will look at the others. So process variation, as I have said, because of light, because of dopant density, right? So when you're placing atoms, what do you want? You want at all the places that, let's say the silicon is exposed, let's say n atoms go through. But one atom is a very small quantity, right? It's a tenth of a nanometer or half a nanometer maximum. So the point is that you can never achieve such a uniform dopant density that you will assume, or you can assume, that the same number of atoms are going to seep in. So that will lead to some manufacturing related process related variation, which will vary, of course, die to die, different dies, different wafers, and within the die, like within a single CPU, you will have some variation, and you will have some variation even at a very small scale, like even in, let's say, 10 transistors, you will have some variation. So you can broadly divide it into two parts, systematic and random, where systematic are basically, these low frequency variations throughout the die, like a high region over here and a low region over there. And random is something that you see even at a very small scale, right? One transistor will fundamentally be different than the transistor beside it. So that's random variation. We'll discuss the reasons behind them, but these are the two broad types. Then we can have variation in the supply voltage, which is a broader part of the parameter variation umbrella, where we could have IR drops because it's a high current drop where the power grid will have an IR drop. And as I said, LDIDT drops. So we can call it LDIDT, which is because of the inductance. So because the power grid has an inductance, by the Lenz's law, it will oppose any change in current, it will apply a back EMF, which will cause issues with the supply voltage. And then of course temperature. So go back to chapter 12, you will have high temperature regions, low temperature regions, and then different temperature values lead to different transistor speeds, which lead to different values of the leakage. So the leakage feedback loop also comes into play, but fundamentally, by and large, the temperature variation across a chip will impact the performance, right? Because in general, higher the temperature, higher is the leakage. For some technologies, transistors speed up, for some others, they slow down. But in any case, this does lead to variation, and a combination of all three is quite deadly. It's called PVT variation, process voltage temperature, all being a part of the overall parameter variation umbrella. So if you look at systematic variation, which was like this component of the process variation, so this is a graph that we generated. So we divided a chip into million grid points, and we kind of have the leakage power variation map in arbitrary units. So you can see systematic regions of, let's say, low leakage power, high leakage power. High leakage power basically means a low threshold voltage, right? That's what it means. So again, you see these systematic regions, right? So this, let's say this region, these are all systematic variations, right? So because there is a correlation in space, and this is happening precisely because of the wave nature of light and diffraction and so on. Let us now look at the sources of systematic variation. There are primarily two. One we have been talking about quite a bit, which is the wave nature of light. But there are other simpler sources as well. So let's look at the first one. It's called chemical mechanical polishing, or CMP. So CMP is it's a bona fide part of the chip manufacturing process. So what happens is that in a large wafer, all the areas are not filled with silicon or not filled with wires and transistors and so on. There are some empty areas, mainly because we couldn't place anything there. So what happens is that in subsequent processing, these empty areas are soft. They are not filled with metal. So these empty areas, can sort of get squished. So there is a need to look at each of these areas and kind of bolster them, increase their structural strength. So to increase their structural strength, what is done is, if this is an empty area, we kind of create these cuboids of copper, cuboids of metal. Of course, they are not connected and they are not charged, but essentially these are like columns whose main job is to hold the area and give it structural strength. What happens whenever we do a metallic fill is that there is a need to kind of smooth it out, and such that the entire layer roughly has the same thickness, right? So in this case, fundamentally, we are altering the thickness of the layer for even other things like photoresist and etching and so on. Along with this filling, we are changing the thickness of the layer, so we would like to homogenize it. So to homogenize it, what we do is we polish the surface both mechanically, kind of grind it, and also we use chemical solvents. In spite of that, because of the varying mechanical properties of the layer, the thickness, if I were to look at a cross-sectional view, would be something like this, right? It would not be uniform. In spite of doing these fills and so on, and in spite of chemical mechanical polishing, the thickness will not be uniform. So we will have a layer with varying thickness. So the thickness would vary regardless of whatever we do. And this would be a systematic variation. There would be a spatial component to the correlation. This would be a systematic variation. And this variation arises after the chemical mechanical polishing process is over. Hence, we call it CMP related variation, even though the real reason is that not all parts of the silicon are equally strong. We try to make some parts strong and then we try to polish, and after all of that, still some variation is left in terms of the thickness, and that leads to a variation in electrical properties. Ultimately, that's the only thing that matters from a high level, variation in electrical properties. And this in this case arises because of varying thickness. Now, if you look at the wave nature of light, well, we are aware of what we studied in our class 12 physics, that the wavelength of light lambda is much larger than the feature size as we have been arguing. So there is a Rayleigh resolution limit beyond which we can't fabricate reliably. So this is lambda divided by the numerical aperture. So a lot of tricks are done to change the numerical aperture and so on. But pretty much when we go below the Rayleigh resolution limit, we'll not be able to fabricate our structures accurately. Corners will get rounded, lines will not remain straight. The wave nature of light will become apparent, right? So these photolithographic effects, primarily because of the wave nature of light, are systematic in character. There is a spatial correlation. Hence, this is the second source of systematic variation, both this as well as this. Random variation, on the other hand, happens for a diametrically opposite reason. We had a problem with the wave nature of light. Now, lo and behold, we have a problem with the particle nature of light as well. So, how is this problematic? Well, it's problematic like this, that if I want to fabricate a smooth line, then what I need is I need a uniform photon flux throughout the line. But a photon, if you think about it, is a discrete fundamental particle, right? Say a photon might strike here, may not strike here, may strike here, may strike here, but then the next one may be here. So the photon flux will not be regular regardless of whatever we do. And this is a straight corollary of the particle nature of light. That's the reason fabricating a smooth line is tough. The edges will have what is called line edge roughness, or LER. And this will arise the moment because light will not fall regularly. So the moment we expose the photoresist to the light and we etch it out, we'll simply see lines with very, very irregular edges. And this will contribute to random variation because, as you can see, this is not systematic, but even neighboring transistors will have different values for their line edges. And that would manifest in different electrical properties as well. So again, the atoms and placement becomes important. You consider a 5 nanometer feature, it's 50 atoms side by side. Can you ever achieve this level of accuracy? Well, you won't be, because this means that if, let's say, I have a small exposed area of the silicon, there's no photoresist here, I want exactly 50 atoms to kind of seep in and create a doped region, which is, let's say, n-type doped. That's not going to happen, right? How do you say? You need very, very uniform dopant density, right? And even for the gate thickness, let's say the gate thicknesses are very low, incidentally. The silicon dioxide layer is only 2 to 3 nanometers, and it's very hard to have this kind of process control that it's exact. And when it's not going to be exact, you will have varying electrical parameters even across neighboring transistors, which would basically lead to Random variation, because after all, at the atomic scale, things are very uncertain, right? So there is a degree of non-determinism and uncertainty. Recall the Heisenberg's uncertainty principle. And that is why placing them so accurately is difficult. So the examples would be like this, that look, this is an example of a systematic variation where we don't have a sharp corner, we have a rounded corner, right? So you just see the rounding. So this is all systematic variation. Random variation will be line edge roughness, which is this. There is an additive nature of process variation in the sense that any component, right? Anytime we see something like the threshold voltage or something, we can roughly divide it into additive components. It's approximate, but works quite well. We'll have a die to die variation plus a within die variation. Whatever is the parameter, del P is any parameter of interest. And die to die, it is die to die plus the within die can be broken into two parts, the P random and systematic, right? Random part, systematic part, die to die part. So let's now try to create a mathematical model to model variation. So we have seen the alpha power law. The alpha power law we have seen earlier, and I would like to bring that forward. So we had seen this in the DVFS part, in the ED square part. The gate delay is essentially proportional to the effective channel length, right? So it's not exactly a channel length, but you have to look at the depletion regions and so on. So there's a term called an effective channel length. The supply voltage, the mobility of the carriers, which is typically varies as temperature to the power minus 1.5, which means higher the temperature, lower is the mobility, especially in silicon, right? And then V minus VTH to the power alpha, right? So V is again the supply voltage, the threshold voltage, and alpha is a constant, which is why this is called the alpha power law, because alpha pretty much tells you how this would behave. In older days, of course, VTH was far smaller than V and alpha was roughly 2. So this was basically roughly V by V square, which is 1 by V. So essentially it was inversely proportional to the supply voltage. That's not true now. So the threshold voltage furthermore, the VTH, can be modeled as VTH 0 minus 2.5 millivolts. So let me assume that the unit is millivolts multiplied with the delta T, the change in temperature. So let's say temperature increases by 10 degrees Celsius or 10 Kelvin, same thing. The threshold voltage, which is normally 100 to 150 millivolts, would decrease by as much as 25 millivolts, which would change the character of the circuit quite drastically. So what happens is that with higher temperature, right, the mobility goes down, right, the VTH goes down, but because it goes down, minus VTH kind of goes up. So this factor over here goes up. So essentially there are two opposing factors, the mobility going down and V minus VTH to the power alpha going up, because alpha is between 1.1 and 1.5. So these opposing factors don't really, you have to see which one dominates, whether they cancel each other out or not, and which one really dominates. In some cases, as I said, with higher temperature, the circuits can get slower or faster. It all depends on the mutual balance of the mobility and V minus VTH to the power alpha. So in general, there is kind of a consensus that at least in conventional technologies, with increasing temperature, transistors slow down. Right. So that's sort of a consensus, but again, as I said, with different technologies, this changes, right? So this is, always look at what these factors are for the current technology, but don't take this statement in face value. So then the gate delay is pretty much, as I said, dependent on these factors. So keeping them in mind, let's move forward. But the important part is that as I increase the temperature, the threshold voltage goes down, which basically means the leakage power goes up, right? So increasing temperature increases the leakage power, which further increases temperature, so on and so forth. So systematic variation, basically, the model that we'll discuss is the Varius model. The Varius model basically says that the VTH and the effective length of the channel are linearly related to each other. Furthermore, it assumes that the variation in the effective length of the channel is half that of VTH. So just computing the variation of VTH is good enough. So from the ideal parameters, let D be the deviation. The VTH will be VTH 0 plus some deviation into VTH 0, right? So basically we'll see what this deviation is in a second. But the key idea is that the threshold voltage at any point of time, let's say that D corresponds to change in temperature, then it would basically be, some constant into, some deviation on top of VTH 0, right? So this is the baseline, and on top of the baseline, there will be some deviation, right? And or let's say that the deviation would be because of voltage. So again, it will nevertheless be a deviation, and this factor D is the important one. So to compute it, what we do is we discretize the surface of a die into a 2D grid. So we have a lot of cells, n cross n cells. So we say that let X be a vector that contains deviation for each grid cell. So deviation in this case is a dimensionless quantity. Let this just be the deviation for each grid cell. See, if this is 0 means that the threshold voltage is same as the baseline. If it's, let's say, 0.1, it means it's 110% that of the baseline. So let's just be a deviation. It's a dimensionless quantity. So in this case, if you have n square, n cross n, if you have n square grid cells, then X will have n square elements, right? It will be one huge column vector with n square elements, where each element contains the deviation. Now what I do is that what I can do is I can assume that the elements are sort of distributed normally, right? So we'll have a covariance matrix. So this is a standard multivariate normal distribution, where this is kind of like a, a multidimensional version of the standard Gaussian or normal distribution, where, as you can see, we have the same parameters, just designed slightly differently, where this is the determinant of the covariance matrix, the inverse of the covariance matrix. So we have a mean matrix over here where x minus mu transpose, this is a classic bilinear form, where we have x minus mu transpose times this matrix times x minus mu. So again, for a simple 2D case, it becomes a regular Gaussian, but this is a multivariate case. So this basically says, which is a reasonably accurate assumption, that the vector x, where this comprises the deviation of all the cells on the die, follows a multivariate normal distribution. And furthermore, there is some spatial correlation which we will discuss in a second. So the spatial correlation basically says that if there is a deviation in one grid cell, it is kind of related to the deviations in the adjoining grid cells. So given the fact that we have this, so let me just discuss the terms again. Mu is the mean vector, sigma is the covariance matrix. So we assume that the covariance, right? So of course, I'm assuming a little bit of statistical background here. The covariance is isotropic in the sense it does not depend on the direction, or it is the same in all directions. The assumption that we are making is that it only depends on the Euclidean distance between two grid cells. First is independent of the directions, same in all directions, this way, this way, this way, all same. The covariance of these deviations across two grid cells is only dependent on the distance between them. That's it. So rho uv, which can be defined as the correlation, the classic correlation, right? This is a Pearson's correlation, is essentially the covariance of two random variables divided by their variances. So most of the literature in this area actually talks in terms of the correlation, which you can see is very nicely related to the covariance. It is basically covariance divided by the product of the standard deviation sigma u and sigma v, where the standard deviation is the square root of the variance, right? So we will now discuss, so this correlation structure is, needless to say, related to the covariance structure. And the correlation structure basically says that the deviation d at any grid cell is in a sense related to all of its adjoining grid cells. And overall, the overall distribution is multivariate normal, but there is some sort of a spatial correlation because we are talking about systematic variation in this case. So before I proceed to the next slide, which is slide number 52, I would not blame you if you don't understand anything of what I just said, because this requires some background in statistics. So before I proceed, let me tell you what is it that you need to understand, let's say the last 1 or 2 slides, and definitely the next 5 or 10 additional slides. So as I said, this part is mathematically slightly heavy, and I really won't blame you if you are not able to understand. But let's look at the concepts. Variance, standard deviation, mean. The normal distribution, the regular Gaussian as well as the multivariate Gaussian, right? So that's important, right? So the multivariate Gaussian would use a determinant and complex stuff. Then, of course, we would like to understand the covariance and the correlation. So this much of basic statistics is required to understand it. So in layman's terms, what we are doing is that we are saying that, look, if I consider the threshold voltage at every point of a grid, so I've discretized the dye surface into the grid, at every cell, right, at every single cell, let's say at this cell, there is a deviation. If the deviation is 0, it means that the value is same as the baseline, but otherwise there is some deviation. So if I consider all the values in entirety, it follows a multidimensional or a multivariate Gaussian distribution. In a sense, it is normally distributed with a certain covariance structure. So this is important. This is a very important addition to this distribution. What is this covariance structure? The covariance basically says how the values in adjoining cells are related. This is perhaps the only thing that you need to understand even though your statistics is weak. So this covariance basically in a sense captures the spatial relationship. And the covariance is very well related to another related concept called the correlation. And they are related like this, that you just divide sigma uv, which is the covariance between random variables u and v, which in our case is basically the relationship or the covariance between the deviations at location u and location v by their standard deviations. You will get the correlation. The correlation in general is a better term to work with because it is dimensionless, right? And the correlation, as I said, is kind of, we can think of it as a proxy to this covariance here. So typically a spherical correlation matrix is used, or a spherical correlation relationship is used to characterize the correlation structure in a systematic variation, in an environment with systematic variation. Again, I did use a fair amount of loaded statistics. In case you were not able to understand, kindly look at all of these concepts and come back to these slides again. These are simple concepts if you have the statistical background. And if you have been able to pick it up, you should have no difficulty in understanding this slide and the next one. This is what the next slide looks like. Let's make an assumption which is reasonably well founded in practice, that the standard deviation is the same for all grid cells. If this can be assumed, which as I said is not a very bizarre assumption, we can say that let this be sigma sys or sigma systematic. Now if I look at the covariance and correlation matrices, then I can simply use this equation over here and say that the covariance uv is sigma sys square. Why sigma sys square? Because sigma u, sigma v, but both are equal to sigma sys, right? This is sigma u is equal to sigma sys and sigma v is equal to sigma sys. So sigma cis square times rho u. So for Varius and many of the other tools, the correlation matrix is important, and it uses the spherical correlation function, which basically says that given a grid cell, I kind of divide the grid cells into two worlds, one within a distance of r and one outside a distance of r. Outside a distance of r, this correlation is 0, which means you can think of them as like absolutely uncorrelated, covariance is 0. And within a distance of r, you can basically say that it varies as per this cubic function 1 minus 3r by 2 phi plus r cube by 2 phi cube, right? So sorry, not within a distance of r, within a distance of phi, I stand corrected. So let me explain that part again. So what I do is I divide all the grid cells starting from the point that I'm interested in into two types. One within a radius of phi and the other one's outside a radius of phi. So if r is greater than or equal to phi, then I say that the correlation is 0, they're uncorrelated. But within a radius of phi, I make it vary like this. This is called a spherical function because you can look at the cubes over here. So we say that there is a spherical distribution, which I think, okay, I don't think I've plotted it, but pretty much, this would look like a regular cubic function. And incidentally, when r is equal to phi, this value would become equal to, when r is equal to phi, this value will become equal to 0. But the key idea is that there is a degradation here. And the correlation function is very interesting in the sense that it basically says that as you keep on increasing, so let's see what happens if r is 0. So if r is 0, then this term is 0, this term is 0, the correlation is 1, right? Which means this is the highest possible correlation you can have. And then we have a decreasing function. And finally, it decreases down to 0, which means that you are the most related to the cells around you. Then you are slightly less related to the cells slightly further away, so on and so forth. So the spherical correlation matrix essentially determines the covariance structure, and the covariance structure directly gets fed into here, into the overall multivariate normal distribution. So this is how the entire systematic variation matrix is modeled. So if you were to actually plot this function, the way that this function would look like is very interesting. If this is the x-axis and this is the value phi, right? And this is the, right? And of course, r is varying this way, and this is rho r. It would pretty much look something like this, where it will become strictly 0. So this value, of course, is 1. And then it will become strictly 0 at phi. So what we can see is a reducing correlation with the radius gradually kind of smoothing out to 0 at the end. So random variation is slightly easier to model. We don't have such complex math. So L effective and VTH are not linearly related anymore. So they are modeled as separate regular single variable univariate normal distributions, where a simple normal distribution without all of that covariance matrices and so on looks like this, where the regular normal thing, but we have a random distribution parameter here, sigma rand square. So of course, sigma cis and sigma rand are typically assumed to be the same or slightly different, but that's a very process specific thing. But we can combine the systematic and random variation to arrive at the standard deviation for the total variation, which is sigma rand square plus sigma cis square, the square root of that. This is a standard variation combining formula for a sum of Gaussian or normally distributed random variables. This is the standard formula that you get. So how would you use Varius for statistical timing analysis? So mind you, we are introducing this term for the first time. This is very different from static timing analysis. It is statistical timing analysis. The reason being that, let's say I have a sequence of gates like this, I really don't know how long a gate will take, right? It depends upon its systematic variation component, random variation component. But whatever is the delay, we can come up with some distribution of the delay. So the assumptions are that let's assume sigma sys is equal to sigma rand. That's what Varius assumes, but again, it's not a hard and fast assumption. And let's assume that sigma total divided by mu is 0.09, right? So then we know how to compute sigma sys and rand from the previous formula. So essentially consider a large number of process variation maps, compute the systematic component using the spherical correlation, compute the random component. Then what we can do is, for a given functional unit or for a given set of gates, we can assume it's fairly small, so it will have a constant systematic component but a varying random component. So essentially, if this takes a random amount of time, this takes a random amount, all of these are normally distributed, then essentially the sum of random variables is also a random variable. So we can model the timing paths as normal distributions. And as I said, the sum of normal distributions is also a normal distribution, where the mean is the sum of the individual means and the variance is a sum of the individual variances. Of course, you can have multiple timing paths in a circuit, and one of them will be the critical path, so we can take the maximum. But here is the point to note, that the maximum of a sequence of, or the maximum of a set of normally distributed random variables is not normally distributed. So it can follow, it typically follows a Gumbel distribution, but again, it's not normally distributed. There are approximations, but it's not normally distributed. So with this, with some critical path information and some assumptions, we can arrive at the distribution of the delay of the circuit for a given variation map, which basically means for the circuit, we assume a constant systematic component because, well, it's not the full circuit, but a part of the circuit or some functional unit. We assume a constant systematic component. And for the random parts, as I said, we just sum their delays up. And a sum of Gaussian delays is also a Gaussian delay. So essentially, normal distribution, Gaussian distribution are the same. Hence, the terms are being used interchangeably. Of course, as I said, I won't blame people for not understanding this. There's a lot of probability and statistics. And finally, we find the critical path, the longest path, and the longest path is essentially the maximum of Gaussian variables, which is not Gaussian. So now that we have the math established, people can take a deep breath. The hard part is over, right? So whatever is left will kind of go soft on people. So as I said, for systematic variation, the only thing that needs to be done is generate thousands of systematic variation maps and ensure that a given circuit works for all of them. For random variation, instead of static timing analysis, we need statistical timing analysis, which, as discussed in the previous slide, you find the delay distribution of a gate, add the normally distributed random variables. You will find distributions for every path in the circuit, find the maximum of these random variables, where a random variable is the delay of a path. So essentially, it's the max of a bunch of path delays. So let's say path delay for path I be pi is the max of pi. And that would basically give you some sort of a distribution like this. And then you choose a safe point and set that to be your clock period, right? So be conservative in this. That is how you would take care of random variation. And systematic variation, as I said, a lot of simulation is required. Now the key point is that now I have combined systematic, I have combined random, I have some idea of the distribution of the worst case delay, and I have chosen a frequency. All of that is very good. But the fact is that if I don't do anything to cut the source, which is if I don't do anything to reduce the variation, what will happen is that my frequency will go down. I'll be too conservative, and my frequency will have to be set to a value which is quite low, and I will lose a lot of performance. Hence, I should look at methods to basically reduce variation as much as possible. So let's look at a few strategies. One of the most effective strategies is optical proximity correction, or OPC. What I do is, instead of, if let's say this is the shape that I want to fabricate, instead of trying to fabricate this, I try to fabricate another shape, which means I pre-distort the shape such that what is printed on silicon is similar to this. So I try to print this, and then so I take this, then I kind of pre-distort it as per a known algorithm. And once I do that, I arrive at this. As you can see, the corner, just because the corners are rounded, I add more silicon at the corners. Just because this corner, you can have more light, I kind of take some silicon away. So I create this structure out of this. Now when I try to print it on silicon, I'll get something closer to what I originally wanted. So the pre-distortion in a certain sense is helping me. I could do other things as well. Let us look at few of the other mechanisms. So one is off-axis illumination. So what happens is that we have a mask, then we have a light source where light falls on the mask. So the parts that allow the light to pass through, essentially an image is formed, and then the lens focuses it on the wafer, right? So that's how it works. So traditional knowledge would suggest, or conventional knowledge would suggest, that if, let's say, this is the mask, the light source should be at the center. So then, that's when the maximum amount of light will hit it, and that's when the maximum amount of energy will be transmitted to the wafer. But sadly, in the nanometer world, a central placement is not the most efficient. Instead, you want to place it slightly to the side, which is off axis. So what happens is that because of the phenomenon of diffraction, more diffraction orders, right? So what happens in diffraction, if you see the side view, then a lot of signal at the center, then a little bit more here, this. So essentially I can capture more diffraction, then the other side is also like that. So I can capture more orders if, let's say, go slightly off axis as expect in comparison to slightly being on axis. On axis would be something like this, right? So in this case, I would capture more diffraction orders. In a sense, more light will actually hit the wafer if there is a slight amount of displacement, as opposed to placing it on axis, which kind of is counterintuitive, but as I said, in the wave world, many of these things actually start making sense. The other is sub-resolution assist features. So what happens is that if I just, if, let's say, this is the shape on my mask, then what will actually get printed will be something like this, right? So perhaps something like this. So this basically means that light is kind of not hitting this region, right? And even if it's hitting this region, it's still kind of irregular. So of course, you can say that I can use optical proximity correction, or OPC, and try to fabricate something like this. But what I can also do, the other approach, is to have these tiny features over here, which literally are tiny, in the sense that nothing will get printed here, right? The main reason being that they're very, very narrow. But some light would still escape, and that light would kind of hit this region over here. That would create a fuller feature, and this would appear somewhat like this, somewhat very, very rectangular-ish. So because it will be somewhat like a rectangle, and this area will get some light because of the assist feature, and the assist feature itself will not be printed because it is sub-resolution. Sub-resolution meaning that it is smaller than the smallest feature that you can print. So it will not like by itself contribute to the noise, but will have helpful effect on the nearby or adjoining structures in the sense it can fill up for the shortfall of light. So in this case, as I said, instead of a dog bone like shape, it will kind of be slightly fuller because of this. Again, a neat idea to increase the amount of light that is available in regions that are not getting enough light. The other is phase shift masking, also known as PSM. So what happens is that, let us say I want to print something, and so then what will happen is that I want to print something here, but this boundary is kind of fuzzy, right? Either it's this way or I have some assist features, but I'm just not able to like create a boundary between two structures. And if they're close enough, what will happen is that they may actually merge, because light from both sides will kind of bring them very, very close. So the crosstalk between them will be high. So what I want is that in this region, right, this region over here, I don't want any structure to get printed. If I don't want anything to get printed, what I can do is that I can have a phase shift material, which will basically shift the phase by 180 degrees. So how can I do that? Well, one way that I can do that is that I can have a varying thickness of the mask, right? Such that, or let's say some other material above the mask, which will essentially ensure that there is a phase shift of 180 degrees. So as you can see, there is some variance in, let's say, this region where there is, and this region. So they are not at the same thickness level. So there is a phase shift, no doubt. So in the intervening region, so this would be like, this would correspond to the intervening region over here, sorry, over here. So here what would happen is that you would have light which is 180 degrees out of phase. Because it is 180 degrees out of phase, instead of this structure, both the structures would still look like this, because some additional material was, something additional was happening in between both, which was essentially this region over here. But then I kind of sent light that was 180 degrees out of phase. Because it was out of phase, there was destructive interference in these regions. So effectively no light reached here. As a result, the contrast is much better, and this joining that I was seeing, which was basically something like this, right? This will not happen. As a result, this additional crosstalk will not happen, because essentially this region, right, gets kind of cut out because of light which is 180 degrees out of phase. So this enhances the contrast. Otherwise, what will happen is if both get together, you'll have a lot of crosstalk and other faults, or they may just get connected. But that's not going to happen because of the phase shift masking technique. So essentially what we are doing is that our mask has a varying thickness or could have a different material which is inducing this phase shift, hence the name. Architectural solutions are no doubt possible. So different regions of the chip could have different degrees of variation. That of course goes without saying. So this would be the systematic component of variation. So what I can obviously do is I can do frequency binning, which is that essentially, take a large wafer, cut it into dies, and essentially see their maximum frequency. So different uh, dies or different chips that come out of a single wafer would have different frequencies. I can just measure at what frequency is working correctly and assign that. Create separate DVFS tables and create dedicated voltage frequency islands within the chip. So what I can do is, let's say even given a single chip, I can say that look, this part, so maybe it could be a set of cores or cache banks or whatever, run at a certain voltage frequency pair. Another region runs at a different voltage frequency pair, so on and so forth. So we have discussed parameter variation and some broad ways of looking at parameter variation. I would just like to add one more thing before I go to the next point, which is hard errors and aging. So one more thing that can be done is called body biasing, or let's say adaptive body biasing. Let me just tell you in a second what it is. So it could be, adaptive or non-adaptive. We will discuss both. So the idea is very simple. The idea is that I can have regions of the chip, and in regions of the chip, I will, let's say, because of my systematic component, I'll have a certain variation and certain threshold voltage. But the threshold voltage is sensitive to, or is a function of, the body to source voltage. So what I can do is that I can change the body to source voltage, which will again impact the threshold voltage, which again, can make the transistor faster, or can make the transistor slower but less leakier. So I can move a transistor in both the directions by changing the body biasing value. And also I can have different supply voltages for every place. If not, maybe perhaps the same frequency, but different voltages to compensate for the variation. So these are knobs that are available to me. So what are the knobs? I can set the frequency of each region, the supply voltage of each region, the body to source of each region. This can help me compensate to a large extent to whatever damage process variation, and later on at runtime parameter variation has created. So coming to hard errors and aging, we need to understand that processors age over time the same way human beings age, albeit in a somewhat very, you know, complicated fashion. So we look at by far the most common aging mechanism as of today, which is negative bias temperature instability. So what happens is that in the silicon substrate, in the silicon chip production process, hydrogen is extensively used. So many of the silicon atoms, which are kind of at the surface of the substrate, just below the SiO2 layer, will have hydrogen atoms there, and will have SiH bonds, including a few, silicon, if you would recall, can make 4 bonds. Maybe some would be with hydrogen atoms, some with, of course, other silicon atoms, but there could be a few dangling. All right, so where basically, it is searching for hydrogen. So now what happens is that when we have a negative charge, because it's a negative bias, protons, which again, are there in the system because of hydrogen, move towards the surface, right? So they kind of move here, 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 just move up. They remain in the surface, and the moment they find a dangling silicon bond, they combine with silicon here, and they kind of get incorporated into the silicon lattice, right? So this is the way that proton, and many protons also just come and they kind of remain unattached. So this leaves a net positive charge on the silicon surface, which in terms of protons, and the negative and the gate on the other side, which of course I'm not showing, in this case is a negative bias. So recall that this would happen for PMOS transistors primarily. It would not happen to NMOS transistors, right? So in PMOS transistor, the gate has a lower voltage. In NMOS, at least as compared to the substrate, it has a higher voltage. So what would happen is that, as we have seen, the positive charge because of the silicon atoms. So if this is the substrate and these are the regions, so there's a net positive charge over here. This is the SiO2 layer. So once you remove a gate voltage, what will happen is that of course this will go back, but this phase is known as the stress phase, right? So because what will happen is that so let me repeat this once again. What really happens is that because protons move up and they find a stable home over here, because they can sort of get incorporated into the silicon lattice, they stay there. And this leads to an accumulation of positive charge, and this is known as stressing. Why stressing? Because you are permanently changing the charge equation over here by having positive charge accumulated. Even if I remove the stress, which means that even if I disconnect the supply, some of the modifications in terms of protons getting absorbed into the lattice would still remain. As a result, the threshold voltage would kind of at least change, right? Some effects can be reversed and some effects are permanent, but some change will happen to the threshold voltage, which is kind of akin or similar to aging. Once, of course, we remove the gate voltage, you can argue that some of the protons should kind of get, out of the silicon lattice and then should go back and so on. Some of that does happen, but some damage is still permanent, which is why we say that this is an aging effect. So T stress is the time for which the gate voltage was negative with respect to the source. This is the stressing time. This is when the protons are actively moving up. T rec is the time that we give for the recovery. So what has been shown, again these are approximate equations, that the change in the threshold voltage delta VTH is proportional to the time that you are stressing for to the power 0.25. So this basically means that it's sort of a weak function of the stressing time, but it's nonetheless there. The recovery, which is again the amount of voltage that you recover, varies like this. It is 1 minus square root of a function times T rec by T rec plus T stress is kind of getting normalized by T stress to in a certain way. But the key idea over here is that clearly the recovery time and the stresses and the T stress time, the ratio is important. But of course, after a certain point, as you can see, when T rec becomes kind of infinite, then this would translate and become 1. So this would become roughly proportional to 1 minus square root of eta. So that essentially tells you that some damage still persists. So similar to NBTI, which is again related to this hydrogen uh, hydrogen molecules breaking and protons coming up, there is another method known as hot carrier injection, which is primarily a leakage current, as we have seen, which is the charge carriers kind of become fast, they gain sufficient kinetic energy to essentially jump the channel gate boundary. So if this is the channel, this is the gate, and you have these carriers, right? In this case, if it's negative, then holes will kind of jump here like this. In this case, protons. And electrons can also come in the reverse way. So in this case, of course, holes and protons are much bigger quantities, so they cannot make a jump. But typically, electrons are the ones that get pushed in. So they can get permanently lodged in the SiO2 layer, right, within the gate. So it can be a transfer either way, this way or that way. In either case, electrons can get permanently lodged within the gate, mainly because they are moving at such a high velocity that they will get trapped in here, a few. Furthermore, what could happen is that they could collide with the SiH bonds at the channel gate interface. And again, they could maybe take the proton out, they could change the chemical structure. So any such change where electrons get lodged here will essentially raise the threshold voltage, making the transistor slower. This method does not show any recovery. Unlike NBTI, in this case, electrons kind of get permanently lodged in here, change its inherent electrical charge. There is very little recovery, and in this case, the change in the threshold voltage is a much stronger function of the time, which is basically the switching time to the power 1.5. So it's a much stronger function. The reason being that this is a fundamentally a more powerful mechanism, but of course here the constants of proportionality also do matter. So ultimately what happens is that after aging and aging, there is a fatal fault. So finally, a fault happens where essentially the system or parts of the system completely break down. So one such fault mechanism is electromigration, which we will discuss, stress migration, thermal cycling, and dielectric breakdown. So all of these are basically, products of aging until you have absolute failure. And the model that will be used to describe them will be the ramp model, the ramp model for hard errors. So hard error means a total, where there's a total breakdown, a transistor or a wire is totally broken down. So that is a hard error. So you can never recover from a hard error. So electromigration, the idea is like this, that if let's say this is a wire, what will happen is that over time, if let's say electrons are flowing in this direction, so they will of course flow, but they will drag a little bit of the metal atoms along with them. So over time, what will happen is one side will become fat and one side will become thin. So this will kind of become like this, kind of like this, right? So this part over here will become very thin. Of course, the resistance will increase, but then it can snap. So basically, it can snap, and then and the fat end can then also go and connect with other wires. So you'll have an open circuit here, and you'll have a short circuit here. So this is known as electromigration, extension of electron migration, where the mean time to failure is proportional to, of course, the current density. This is the current per unit area, normalized, of course. Then multiplied with this term. So you will see many variants of this term for all of these equations. So these equations, incidentally, are known as the Black's equations. So basically, you would need, so they will all be of the form 1 by kT, or some constant by kT, where the constant here is the activation energy needed for electron migration, by K is the Boltzmann's constant, and T is the temperature in Kelvin, right? So almost all of these temperatures, actually for the next 4-5 slides, all of them are in kelvins. So this is the broad equation. So you see, as the temperature increases, the overall term decreases, right? So the MTTF basically decreases as the temperature increases. So what we can say is that with increasing temperature kind of exponentially, the MTTF reduces, or the mean time to failure reduces, or the failure rate increases. This is one more reason why high temperatures are a bad idea. Stress migration, similar idea, but of course here it is not for wires, but it is for contacts. So what happens is, when an interconnect is making a contact, either with the IO pins or with other on-chip structures, then the different parts of the contact could have slightly different materials, so they will have different thermal expansion and contraction rates. So that will create some amount of thermal stresses which can then migrate. So they will kind of migrate throughout the body of the interconnect, because it could be like between two contact structures. So these stresses will migrate, and ultimately stresses lead to cracks, right? So stress migration will essentially lead to atomic migration. You'll again have, thin fats and so on, and cracks, and finally the wire, especially near the contacts, will break down. So if this is the broad idea, so of course in this case the reasons are more mechanical as opposed to electrical. So the equations are similar. So what we basically do is that we take a look at the temperature. In this case, it is subtracted from a very high baseline. We see the same term repeat here also. And the term here, of course, this constant is different. This is for stress migration. For copper interconnects is 0.9. For other interconnects, it will have other values. But this is the constant that we have over here. See, here again, as the temperature increases, the MTTF decreases, kind of in a similar fashion. Again, one more big incentive to keep the temperature low, because this can affect the reliability quite significantly. Time dependent dielectric breakdown. So the idea here is that in current transistors, if let's say this is the channel, right, then the dielectric layer over here is quite thin, right? So the silicon dioxide layer is quite thin. So you have a polysilicon gate and you have a contact. So what happens is that this layer as such is very thin. It's only several nanometers. So because of that, there is a fair amount of electron tunneling kind of through and through. So we have discussed the leakage current mechanisms. So a few were related to tunneling. And here the idea was we had one quantum mechanical tunneling and one more tunneling because of kinetic energy. So in both cases, there is a lot of electron thoroughfare in that sense. So ultimately what would happen is it will change the chemical structure of the dielectric. So it will become more porous to electrons, ultimately becoming a conducting path. So this is known as dielectric breakdown. So here again we have an MTTF number for this, a mean time to failure number. This is of course it's proportional to the voltage. So higher the voltage, lower the MTTF, makes sense because higher the voltage, greater will be the electron flow. And then this is a complex function of temperature, but the basic idea is as temperature increases, the MTTF of time dependent dielectric breakdown, this reduces and this also reduces quite considerably, right? So that is the idea. Thermal cycling, this is exclusively for the solder joints. So where you have the solder joints in the packaging, right? So where it is kind of connected to the rest of the board. So these solder joints experience expansion and contraction. Ultimately, as I said, they develop cracks, then they have metal fatigue and they fail. So this is true for all kinds of metallic joints. It's just not limited to solder joints, but if you consider solder joints and their unique alloys that are used in the solder joints, then of course you will have expansion, contraction, and you will develop cracks. And the constants will be different in the equation, but broadly, if this is the mean time to failure, again it's a function of the temperature. Higher is the temperature, right? Lower is the mean time to failure, which is a bad thing. So in this case, Q and T ambient. So T ambient is basically the ambient temperature, the outside temperature, right? The normal temperature where you have the chip in the room without the heating effect of the chip. Q is an exponent and T is the temperature, and the relationship is quite obvious. It's in fact it has been like this for the last few equations as well. So if you look at processor failures because of a combination of all of these mechanisms, hard errors, which is kind of the end point of aging. But in aging, of course, we didn't discuss the interconnect models, but in hard errors, we discussed the interconnect models. Aging was more about a reduction in a transistor's life, right? That was what aging was about. But in any case, if we kind of take the sum total of everything, we will see that there is this infant mortality phase, which means that some processors which have design defects, let's say a lot of variation or so on, they would fail at the time of burn-in itself. What is burn-in? We have discussed this. So after a chip has been packaged, in some cases before it has been packaged, it's kind of taken to an oven. There you really raise the temperature and then you do testing over there. Then what happens is many of these faults kind of become more visible, more prominent. They kind of come to, they can, in a sense, they come out of the closet. So you can clearly see that if in an extreme region, right, are any faults coming out. If that's the case, the chip is discarded. If a chip passes this burn-in part, it will have a normal life for quite some time until ultimately aging takes over and some or other hard error happens. So a chip normally has a 7 to 10-year life. So you can have many failure rate models. You could say it is exponentially distributed, normally distributed, but typically exponential and log normal are the most common distributions, where a log normal distribution looks something like this with a heavy tail. So this captures the infant mortality part. Sorry, I mean, including the peak, this captures it. And then, of course, gradually towards the end, ultimately it fades. So you can assume that a processor with many parts is a series failure system, especially if you don't have any redundancy. So if any one of them fails, the entire processor goes. So what are the methods to as such tolerate hard errors? Well, the standard method is reduce temperature. So reducing temperature, very dramatically reduces the MTTF, mainly because of the expressions that we saw, and we saw the exponential relationship of temperature. The other is that, to stop electromigration, if let's say this is your copper wire, you, in a sense, you give it a coating, right? You give it a covering. of something like tantalum nitride. So what this will do is, in a sense, it's kind of hold the wire together, right? It's like putting the wire in a hollow cylinder where the cylinder is tight. It will not allow parts of the wire to kind of fatten up, and you will not have extrusions and short circuits. Extrusion is basically part of the wire coming out. It will kind of hold the wire in place. It's more like, some sort of a restraint. So this can be done. It will stop the diffusion of course, copper items in nearby structures. And if a part of the wire doesn't get fat, then the other part will automatically not get thin. So it will limit the effects of electromigration. Other is that in the memory, you keep a few additional rows which are otherwise unmapped. But let's say, these three rows are mapped, but this row is not mapped. If any one of the row develops a fault, then kind of you have a smart decoder which will remap this address to over here, such that this the backup row will have the data for the original row, because the original row is not out of service, right? It developed a fault. You decommission it, so something like virtual memory, you remap it to another row. The other is that if possible, you work in a degraded mode, which means that you reduce the number of cores or you reduce the number of functional units. So if let's say one adder develops a fault, try to survive with the other adder. If there are 8 cores, 4 develop a fault, run the processor with 4 cores, so on and so forth. This is the last slide. We always love to see this slide. So we discussed 5 main things here. First, we discussed transient errors and soft errors, which were particle strikes due to neutrons or alpha particles, which create a current pulse which flips a bit. Then we discussed inductive noise, which is basically when there is resonance because of the chip's activity and the inherent resonant frequency of the power grid. That is when the impedance gets maximized and you have voltage spikes, and these spikes can be quite damaging. So they can make transistors very slow and you may have timing faults. We could have design faults in processors, plain old bugs. Many a time compiler writers, OS writers issue workarounds and patches, which in a sense handicaps a part of the system such that at least one of the conditions for the bug will not get triggered. Process variation, big issues. We did a lot of math, talked about systematic variation, random variation. Transistors do age over time. We have HCI and NBTI. So these are of course transistor level models. There are interconnect level models, including hard errors. Hard error is the final. So finally, when an interconnect completely gets snapped or a transistor completely dies, it results in a hard error, right? So that's the reason it's an error, it's not a fault. So we discussed their relationship and we understood how important temperature control is in the overall reliability of the chip. Thank you very much. So this chapter ends over here.